Hey everyone, welcome back to Calc 3. This will be part B of lecture 1. So we're right in the middle of discussing and proving a handful of theorems and properties of vector arithmetic, particularly the vector sum and scalar multiplication. So here's another theorem. This says that if v is a non-zero vector in the plane, then the vector u, which is equal to v divided by the norm of v, okay, which we can also write as 1 over the norm of v times the vector v, has length 1 and the same direction as v. Okay, so this is really handy. This means that any vector, we can find a unit vector for any vector using a procedure like this, right? So if v is my given vector, it's not a unit vector, but it's going to have some direction, also clearly some magnitude. If I want to find a vector that is a unit vector with the same direction, then I can use this process. So basically take the original vector v, divide it down by its length, and I get a unit vector in the same direction. Okay, let's prove that this is true. Let's prove this one. And so we would start by saying that, notice, because 1 over the norm of v, right, that's a positive number, isn't it? Right, notice 1 over the norm of v is a positive, right? So 1 is obviously a positive number. When I take the norm of a vector, it's always going to be a positive number, right? Remember, that's the length. So length is, typically a positive quantity, and in the case of vectors, we would want to think of length as being positive, right? And so because 1 over the norm of v is positive, and we would say that u is equal to 1 over the norm of v times the vector v, it's going to be clear that u would have the same direction as v. Right now, hopefully that's clear. Maybe we can discuss it a little bit here. So if I have, if this is the plane and I have some vector v, if I multiply v by 2, for example, then what do I get? Well, I get the same vector. I get a vector in the same direction that's just twice as long, right? Similarly, if I have it, right, I get something that's shorter. Right, so multiplication by a positive scalar, it just changes the length of the vector, makes it longer. If you're multiplying by more than 1, makes it shorter if you're multiplying by a fraction less than 1. Right, now it is possible to change the direction of a vector by scalar multiplication, but that only happens when you multiply by a negative. Right, if I multiply by a negative, it can flip it the other direction. Right, but so long as the scalars are positive, then all it does is lengthen or shorten the vector. It has no impact on the direction. Okay, so that's the idea here for the first part, right? So this 1 over the norm of v is a positive number. Right, it's a positive number. If the norm of v is greater than 1, then this will shorten the vector. If the norm of v is less than 1, then this scalar will lengthen the vector, right? But in both cases, the scalar you're multiplying by, 1 over the norm of v, is positive, so it's not going to impact the direction, right? So u and v will have the same direction, okay, under this procedure. Now, what about the magnitude? Okay, so to see that the norm of u, the length of u, magnitude of u, is equal to 1, here's how we can do it. So note that. Okay, so we start with the norm of u, and let's just write out how we've defined u. So u is going to be 1 over the norm of v times the vector v. Okay. Now, 1 over the norm of v, remember that's a scalar, right? This is 1 divided by some number, so it's just a scalar. Okay, and we just talked about what happens when you take the norm of a scalar times a vector. Right? Remember we said that the norm of a scalar times a vector is equal to the absolute value of the scalar times the norm of the vector. Right? We said that. Right, so that's what we want to apply here. So this is a scalar, so it'll be the absolute value of 1 over the norm of v, okay, times the norm of v. All right, now 1 over the norm of v is positive, so we don't need the absolute values. So this is just 1 over the norm of v times the norm of v. And this is a number, this is the same number, right? So you can cancel, and you can see that the magnitude is 1. Okay, so that's a nice little proof that u defined like this has unit length, is a unit vector. All right. Excellent. Okay. All right. So here, I guess I kind of have been using this term, but here, yeah, when we say u has length 1, we call it a unit vector. And when it's in the same direction as another vector, we say it's a unit vector in the direction of v. So here we say that u is a unit vector in the same direction as v. Okay. This process, this process of, let's see, so this process of multiplying by this 1 over the norm of v, it's called normalization of v. Okay, so basically this, when I multiply times the norm, 1 over the norm of v times v, this normalizes v. Okay, so that's just terminology that we'll hear again and again as we get deeper into this. Okay, so let's do an example using this process, kind of see how it works in practice. Let's find a unit vector in the direction of v equals -2, 5. Okay, so we're looking for a u where u is basically v divided by its norm. Okay, and so we can kind of write this in here. So this will be -2, 5. And what's the norm of this vector? That'll be -2 squared plus 5 squared and the square root of that. So it'll be -2, 5 divided by square root of 29, I think. So this will be 4 plus 25. Yep, square root of 29. So that's 1 over the square root of 29 times -2, 5. Right. So remember, this is the scalar. Right. So scalar multiplication. Right. When we write it like this, it doesn't make a lot of sense to us yet. This sounds like you're trying to divide a vector by a scalar. And we haven't really talked about that. We certainly haven't talked about using it in this form. So just keep in mind that this is just one way to write. The numerator is this vector. The denominator is a scalar. It's really just scalar multiplication, though. So this would be -2 over the square root of 29, 5 over the square root of 29. right? And so this is your vector in the same direction as v. Right, now let's confirm that this has unit length. How would we do that? Well, we could take the norm of it. The norm of -2 over the square root of 29 and 5 over the square root of 29. What's that norm? Well, we just have to square the components, add them together, and take the square root of the sum. Okay, and so we can do -2 over the square root of 29 squared plus 5 over the square root of 29 squared. And then we take the square root of that. And so this would be, so this is 4 over 29, isn't it? Right? 4 over 29, and then this is 5 squared is 25 over 29. Looking good. And you get 29 over 29, square root of that, so 1. Okay. All right. Very good. Okay, so we've talked about what a vector is, different ways to represent vectors. We've talked through vector arithmetic. We've talked about the norm of a vector a fair amount, how to normalize a vector, right? By taking the vector and dividing by its norm. You get another vector which is normalized, meaning it has unit length and it's in the same direction as the original. Okay. Let's talk next about standard unit vectors. Okay, so the standard unit vectors. Okay, so the unit vectors 1, 0, and 0, 1 are called the standard unit vectors in the plane. Okay. They're called the standard unit vectors in the plane. Now, these vectors are used so often that they have kind of their own notation to some extent. They are denoted, it's more of a convention. The first unit vector, the 1, 0, is denoted with an I. And the second one is denoted with a J, like so. Okay, and so you can think of these as, all right, so here's my XY plane, right, and if this is 1, 2, 1, 2, then these vectors lie on the axes and are, and have a unit length. So this is your I, and this is your J. Yeah, that's right, J. Yeah. So you've got your I and your J, right? So this is 1, 2, 1, 2, right? So you kind of see. They have unit length, right? They lie on the axes. Okay. Now the nice thing about these guys is they can be used to represent any vector. Any vector in the plane can be written using I and J. Okay, now how does that work? Well, let's see here. So these vectors can be used to write any vector. And it will say as follows here. So let's see. All right, so say I have a vector v, and it's v1, v2. Okay, we can write that as v1 comma 0 plus v2 comma 0, right? Oh, okay, hold on. I'm running out of space, and I also wrote that wrong. That one isn't correct. Hold on one second. So we start with any vector v equal to v1 comma v2, right? And that can be written as v1 comma 0 plus 0 comma v2. All right, so naturally. Right, so you remember how, if you were adding these two vectors together, it'd be v1 plus 0 is v1, and then 0 plus v2 is v2, right? So clearly that works, right? And you could remember this is, this is basically just a number, and so I could factor it out and think of it as scalar multiplication. So this could be written as v1 times 1 comma 0 plus v2 times 0 comma 1, right? And so what is that? Well, that's just v1, it's a scalar now, times I, plus v2, it's a scalar now, times j. Okay, so that's one way to write the vector v in terms of the standard unit vectors I and j. Okay. Let's do an example. So we'll let u equal a vector. We'll let u be a vector with initial point 2, -5, and terminal point -1, 3. Let's write u as a linear combination of I and j. Okay. Okay, so I'm going to write u as a linear combination of I and j. So first, let's write u. Let's gather the components of u. Right, so u would be equal, so your terminal point is -1, 3, your initial point is 2, -5. And so remember, when we do this, we would want to go, it'd be like q1 minus p1, comma, q2 minus p2. Okay, so it's going to be -1 minus 2, and 3 minus -5. Right, so when we do that arithmetic, you get -3 and 8. Right, so the components are -3 and 8. And so just based on what we just saw up here, it's basically the first component times I plus the second component times j. So you can think of this as -3 times the vector I plus 8 times the vector j. I and j being the standard unit vectors in the plane. All right. Very good. That's very cool. Okay, let's do another example. So given u above, right, the one we just did, and v, let's say, is equal to 2 times the vector I minus the vector j, let's write w, which will be equal to 2 times u minus 3 times v, as a linear combination of I and j. All right. Okay, we can do this. So w, we're saying, is equal to 2 times u minus 3 times v. Okay, so what was u? Well, that was what was above, right? And so u is -3i plus 8j. Okay, and we want to subtract from that 3 times v, which is given up here as 2i minus j. Okay, we want to figure out what all that amounts to. Well, this is, you can basically just multiply through here, so you get -6i plus 16j. Right, that's this piece. And then it's going to be -6i plus 3j. Right? Okay, we add the i's and we add the j's. We get -6i minus 6i, so we have -12i. And then 16j plus 3j, 19j. Okay, and so there you go. Now, it's also possible to write all of this, to convert all of this back into, regular components without standard unit vectors, and combine them that way, and then rewrite them as standard unit vectors. But I think the point in doing it this way is to see that it basically works the same way. If you have negative 3i plus 8j, it's another way to write negative 3 comma 8, right? And if you have 2i minus j, that's another way to write 2 comma negative 1 for a vector, right? You can see if you did all of that, if you try to do it the other way, you'll get the same result. Okay. Very good, very good. All right. Next up. So, if u is a unit vector, such that theta, or talking about an angle, is the angle from the positive x-axis up to u, then the terminal point of u lies on the unit circle and u, the vector, is equal to the cosine of theta. It's the first component. The sine of theta is the second component. It's also known as cos theta I plus cos theta j. Okay, so let's break this down a little bit here. All right, so you may recall from your trigonometry class, right, what the idea of a unit circle is. Right, it's the circle that's built around the origin that has radius 1. Right, pretty much, not all of it, but much of your trigonometry class took place inside the unit circle. Right, and so all this is saying is that if u is a unit vector, right, meaning its terminal points on the unit circle, and you've got theta as the angle between the positive x-axis and u, right, it's this angle, then u can be written as cosine of theta, sine theta as the components. Right, now hopefully that makes sense, right? If you think about this, right, remember this is your sine of theta on the unit circle. This is your cosine of theta. Okay, remember the u is just, it'll be u1 comma u2, right, where u1 is you can think of it as, it's the component, but it's also, the terminal point. It's going to be the coordinate of the terminal point, u1, the x coordinate of the terminal point, and u2 will be the y coordinate of the terminal point. Okay, and so that's also going to be that height, right? So that should make sense. It's basically u1 is this, u2 is that, and so u, written in standard position, is just cos theta sine theta. Right, and then of course this can be written using standard unit vectors. So you could write it as cos theta times the vector I plus cos theta times the vector, sorry, that's sine theta. Cos theta I plus sine theta j. Okay, that should be a sine. Sorry about that. Cos theta plus sine theta. Okay. Okay, now it also follows that for any non-zero vector v, right? For any non-zero vector v making an angle theta with the positive x-axis has the same direction as u. Okay, so it also follows that any non-zero vector v making an angle of theta with the positive x-axis has the same direction as u. Right, so that's just basically what we're saying there is that, you know, if you've got your u and it makes an angle theta, right, with the x-axis, then any other v, or any other vector v that sweeps out the same angle is going to have the same direction as u, right? That's just kind of basic, right? Right. So any other vector v making an angle theta with the positive x-axis is going to have the same direction as u. And we can write, what can we write? We can write v equals the norm of v times cos theta sine theta. That's the vector. That's basically u. And that's going to be equal to the norm of v times cos theta times the vector I plus the norm of v times sine theta times the vector j. Okay. All right. Very good. Let's do an example. Kind of pull some of this trigonometry into the works here. Let's do an example quick. Okay, so the vector v has a length of 3 and makes an angle of 30 degrees, right, otherwise known as pi over 6, with the positive x-axis. Okay, let's write v. Okay, we're going to write v as a linear combination of I and j. Okay. Okay, so we know that v is equal to the norm of v times cos theta I plus the norm of v times sine theta j. Okay, so what's the norm of v? Well, we're told that it has a length of 3. So this is equal to 3 cos theta I plus 3 sine theta j. Okay, and we're told what theta is. It's pi over 6. So this is 3 times the cosine of pi over 6 plus 3 times the sine of pi over 6 times j. And what is cosine of pi over 6? Well, you could go and consult, you know, your unit circle if you have it from trigonometry, or you could pull out a smart calculator, or possibly memorize this one. But cosine of pi over 6 is the square root of 3 over 2. And the sine of pi over 6 is 3 over 2, square root of 3 over 2 as well. Okay. And so what we get here is three times the square root of 3 over 2 plus 3 times the square root of 3 over 2 j. Okay, I plus j. Okay, and so we've written this given vector. Well, we weren't given a vector, but we were told some properties of the vector, and we kind of plugged it into this expression here. Okay. All right, so I know that was a lot of information, right? This opening lecture. We're kind of trying to level set on vectors. So key things to remember here are what is a vector, clearly, and then, you know, how to write vectors, some of the different, you know, approaches to representing vectors, so component form, directed line segments, etc. Vector arithmetic, right? Particularly vector sums and scalar multiplication. Okay, properties of the arithmetic, right? So namely, you know, associative property, distributive property, you know, the additive identity, the zero vectors, you know, all of those things. There's about eight or nine of them that we talked through. Okay, and then the norm of a vector, and the norm of a vector, and also standard unit vectors. Okay, those are the key things. Right, there are a few other things we talked about, namely like some of the trigonometry at the end here. These are just different ideas kind of tying everything together. Right, but these are the big takeaways. Need to be able to write vectors, add them, subtract them, multiply by scalars. We need to understand all of the arithmetic. We need to know what the norm of a vector is, and we need to have some idea of what a standard unit vectors happen to be, and how to write representing vectors using the standard unit vectors. I should put that on here too. Representing vectors using like I and J. Okay. All right, so that's where we'll end this first lecture. And when we come back next time, we'll basically take this idea of vectors in the plane and move them into three-dimensional space, which basically means we're just going to add a component to them. Okay, we'll be adding a third axis to the coordinate system, which amounts to basically just adding an additional component to our vectors. But most of the other things will remain unchanged. All right, so we'll see you all next time. Take care.